Hello everyone, myself Suryapal representing Satish Chandra Memorial School under Atal Innovative Mission Viksit Bharat program at the rate 2025. Today we are here to introduce a new innovative project that is Agrobot. Agrobot is not just a mere plant monitoring system, it's a companion for the farmers or the Krishak brothers and sisters to cultivate more efficiently. We're introducing AI along with plant monitoring system, which includes different sensors to understand the quality of the soil for the correct sowing seasons. The farmers will get a qualitative and quantitative fictions of the data along with suggestions to do along with it. The farmers won't get any kind of problem to understand the interpretations because they are used by AI. Now let us dive into the dashboard which we have created. The dashboard is first along with the monitoring system. It represents on the growth stage along with the variety. Here we have chosen tomato as a vegetative character along with cherry tomato as its variety. Temperature range is also given, soil moisture along with temperature, humidity, soil moisture, gas level and light intensity in their correct standard units. Under it we can see the graph when it have increased or when it have decreased. This graph gives us the idea when the sunlight or temperature, humidity or soil moisture is increasing, at which time and what to do along with it. Next in our dashboard we have sensor data. This data, when we are connecting with the hardware, it collects the data and registers it accordingly. We have used some data previously by collecting it from the machine. It includes greenhouse air, when the temperature was when, and the humidity along with the soil moisture content. This will help us to understand and analyze it further. This is very important for the farmers to understand that learning about their field is very much important in order to manufacture something of great quality along with consistent quality. Next we are having the most interesting thing of all is the AI assistant. Now we will be asking it about my farm. What do you suggest me to do? The AI assistant is analyzing the data and will give a suggestion based on it. This is a suggestion that it has given. It has analyzed the temperature, humidity, soil moisture, gas levels, light intensity, and also it have introduced what to do and when to do. It told fertilization, pest monitoring, regular checks is very much needed. Also the current reading with the optimal reading and action needed to certify it. Now we will move forward to the plant profiles. In the plant profiles, we can create different kinds of plants. Suppose we have created potato, tomato, and the sweet potato, cherry tomato as the vegetative characters. We can add plant by clicking on this menu and can add the details by here. Now we will move forward to the device control system. Here we have added a water pump which will include controlling it automatic whenever there is needed of water. We are using ESP8266 and ESP32 for this, and also we have introduced the code for connecting it with the Wi-Fi. Also the farmers will get alerts according to the moisture levels, temperature or anything. This is all about the software. I hope you like it. Thank you.
I myself Rajarshi Mandal, 11A Science from Satish Chandra Memorial School will be talking about our hardware part of the project the plant health monitoring system, that is the Agrobot. So in this project you will be able to see the device a few moments in the screen. That in this project we will be using one small device which takes not a great space but will require one of the main component of this project, that is a Wi-Fi connection. It uses a 16:2 LCD display which displays the current parameters we will be recording, on the farm itself for the farmers. Now the farmers will be facilitated with 6 different types of data that will help them to manage their crops more easily. Namely, those are temperature, humidity, soil moisture, light intensity, air quality, and this will obviously help them to uplift their choices in seed patterns, crop patterns, growing patterns, etc. The farmers will get a clear insight into their more farming techniques and practices. Also, we are integrating this data not only to show them to the farmers, but also the soil moisture sensor can unanimously control the pump to start automatically according to the need of the plant. If the farmer wants, we can set up automations accordingly for the farmer in this using this device, that he can set his automations as he likes, as you can schedule anything, or he can automatically set if the threshold value goes up or down, a certain action will take place. The best part about our project is that the farmer can fully customize the automations he can add to the project. In this hardware portion of the project, you will be able to see some of the components that I have covered using the videography. Namely, I have used MQ series gas sensor for the air quality measurement, DHT11 sensor for the temperature and humidity portion, and also we have used LDR sensor for the light intensity part, and the soil moisture sensor module along with its soil moisture sensor external kit that will be embedded into the soil for giving the soil moisture readings. And I hope this project will help the farmers to uplift their crop management techniques to a higher level, as discussed previous by my fellow mate Surya, who has already integrated this part with an AI chatbot to make this project not only strong but also to help this project to achieve greater heights.
Hello, myself Aditya Roy from class 11, Satish Chandra Memorial School. Now let's take this project a step further. So I am using computer vision and trained AI model to monitor the health of tomato plants in real time. The main code imports initial libraries like OpenCV, NumPy, and TensorFlow Hub. We use OpenCV for image processing, NumPy for numeric operations, and TensorFlow Hub to load a retained plant village AI model for disease detection. The camera feed is captured through CV.video capture and the index number. Each frame is processed to detect the plant using color thresholding in the HSV color space, isolating green pixels that represent leaves. Once the plant is segmented, the code estimates several parameters such as height, calculated from the bounding box of the largest counter, and converted from pixels to centimeter using a scale pattern. And then leaf area, which is computed as a total counter area of the plant mask. Then health index determined by the average brightness of the green region, giving a normalized score between 0 to 1. Leaf count is counted by finding individual green counters, and the color index measures how green the plant is compared to the red or yellow tones, which can indicate stress or nutrient deficiency. For disease detection, the system extracts the plant region, resizes it to 224 x 224 and sends it to the TensorFlow model for the prediction. The output is matched to our class list, including the disease names, and the model learns the predicted disease name along with confidence score. All calculated values such as height, leaf area, and health index are stored in a CSV log file, with which the current date is updated every time. Every day, the system automatically takes a screenshot of the plant and logs new data entries though only once per day. We use matplotlib's function animation to create a live graph that updates every second, showing trends in height and leaf area over time. On the live feed camera, we use OpenCV to create HUD or heads-up display, which overlays live text on the camera feed, showing matrices like height in centimeter, leaf area in pixels, health index, and leaf count. Then also the detected disease and the confidence score. We are also adding a health bar, which is shown at the bottom, turning from red to green depending on how healthy the plant is. Finally, the two debug windows shows the plant mask and disease mask, helping us visually confirm segmentation and spot detection accuracy. This system enables farmers and researchers to track plant growth and automatically without manual measurement. It helps detect disease symptoms at an early stage by recognizing discoloration and brown patches through both traditional vision and AI classification. Because it runs entirely on a low-cost camera and computer, it's affordable and scalable for rural farmers. No internet connection is needed for the local monitoring. In the future, we plan to integrate SMS or app alerts for early disease warnings. This combination of AI, IoT, and analytics supports precision agriculture, allowing farmers to reduce pesticide use, improve yield, and make data-driven decisions. It directly aligns with smart agriculture vision of Viksit, where technology empowers every farmer in country. To sum up, our plant health monitoring system transforms simple camera footage into meaningful agricultural intelligence using computer vision and AI. It's practical, efficient, and made for the future of India's smart farming revolution.
Myself Shutrishna Viswas. The plant health monitoring system effectively integrates moisture, air quality, temperature, light, and humidity sensors into a unified platform which can help nurture the growth of crops for cultivation. Provides real-time monitoring of environment parameters essential for healthy plant growth. Enables early detection of unfavorable conditions and disease analysis to foster crop productivity. Promotes efficient water and resource management, reducing waste and optimizing plant care. Enables early detection of unfavorable conditions. Enhances plant growth, health, and productivity through continuous observations. Encourages data-driven decision-making in agriculture for improved crop management. Represents a move towards smart, sustainable, and eco-friendly farming practices.
Myself, Ayush Viswas. The plant health monitoring system provides a comprehensive data-driven approach to precision agriculture by integrating moisture, temperature, humidity, air quality, and light sensors for continuous real-time monitoring. It ensures optimal growing conditions, reduces resource wastage, and enhances crop productivity through intelligent communication and accurate environmental analysis through sensor integration. The system promotes sustainable farming and empowers farmers with real data-based decision-making for efficient plant management. In the future, it can be upgraded with AI-based predictive modeling, IoT-enabled remote access, automated irrigation, and nutrient analysis, advancing towards large-scale smart farming, climate-resilient cultivation, and technology-enhanced agriculture ecosystems.